Datapath functional units. We'll cover on comparator design and shifters and multiple input adders and multipliers. For comparator, there are several different comparators. So zero detectors. So if the input A is all zero, then we detect that detector assert the value. Once detector means if the input is all 1, then we detect it. Sometimes we can equality detector there. So if the input is equal, then we assert it. Or we can have a magnitude comparator. So if the input A, for example, is less than B, then we assert it, right? Or if the input A is greater than B, then we can assert it. Ones and zero detectors. So actual implementation for ones detector, we can have an N input AND gate. The implementation is shown here. If we have an AND. So for bubble, from the bubble convention, we know that NAND gate is faster than the other NOR or whatever. So we transform that logic with a NAND gate in the first stage, and the second stage, this one is NOR gate, right? From the bubble notation, and then the last one will be with NAND gate plus inverter. That will give us the all ones, one detector. For the all zero detector, so if the all input is 0, then we get this. So from the bubble convention, this is equal to changing the shape and then putting all the inversion and in the input and output. That gives us a NOR gate. Last one is the AND gate, so we have a transformation of NAND plus inverter. So this is the actual implementation you can have. On the bottom here, we can have all one detector in multiple stages by comparing only one each, right? Then we have multiple stages. How many stages? 1, 2, 3, 4, 5, 6, 7 stages. Logic gate is required. That is a very long delay path. If we make it parallel comparison there, then we can have only 3 stages logic. But if you include that inverter there, then it can be 4 stage, right? So this kind of a tree implementation is more efficient rather than this is like a sequential logic computation is not preferred for fast operation. For equality comparator, so we'll check whether the two input is equal or not. So we have exclusive NOR there. If those two inputs are the same, then we have asserted. So every bit is asserted, then it becomes A equal B, right? This is the equality comparator. For magnitude comparator, we have to take the subtraction. So B minus A is calculated. So actual B minus A is implemented by 2's complement operation. So minus A is same as inversion of A plus 1. So I'm not sure you guys familiar with the 2's complement number system. So for 2's complement number system, we can have a minus operation with that. For example, 2's complement we map we map the bit, for example 3 bit. So 0 0 0 meaning 0, 0 0 1 is 1, 0 1 0 is 2, so 0 1 1 is 3. Now 1 1 1 becomes 1 0 0 1 0 1 1 1 0 and 1 1 1. So we map the 1 1 1 with the minus 1, and 1 1 0 is minus 2, this is minus 3, this is minus 4, like that. So by having this mapping, the number is continuous around the 0, right? And then we can easily convert minus 1 to plus 1 by inverting all bits and plus 1, right? For example, minus 2 to 1, invert everything, plus 1. That gives us this value, right? This is how we convert the number from positive numbers to negative number. So in actual hardware implementation, to make a subtractor, so we take the inversion of the one input and add 1 to the carry in, and then add them up, and then we can see that the sum here, if the sum is all 0, then A equal B, because of the subtraction result is all 0. So if this mean is 0 or equality, so this is equal case. What if we want to find that 1 is greater than B? So if the C is 0, C carry out is 0 here, meaning A is greater. So this is inverted. So A is greater than B. If the carry out is 1, and A is less than 1. For example, let's do this some operation. So A, we are calculating B minus A, right? If the result is positive, then B is greater than A. So when the result, if how we check if this is greater than 0 or not, or let's say like this. If the B minus A is a negative number, meaning what? B is less than, so B is less than A, right? For example, what would be the case? So B is 1 and A is 2. For example, B is 1, 0, 1, and A is 0, 1, 0. If you want to subtract, make a subtraction there, what we can do is that invert 1, 0, 1 and plus 1. We add them up. So here 1, so carry, so it's 1 and 1, 1. So it will be easier, for example. So we calculate this bottom part first, for example. Then 0, 0, 1 and 0, 1, 1, right? Now calculate 1, 1, 1, right? There's no carry out happen, right? If there's no carry out there, then this becomes a negative number, minus 1, right? So if then the B is let's say B is less than A, right? So A is greater than B, like this. So we can do some magnitude comparator here. For signed numbers, the comparison is a little bit harder. So we are comparing A and B based on A minus B result, right? So C is the carry out, and G is the O0 case if the A minus B is all 0, and N is negative if the MSB of the result is negative, right? So V overflow is the input have the different sign, but output sign is not equal to B. In that case, we assert that overflow. Using all those 4-bit combination, we can check the A equal B condition. That for signed condition 0, check the 0. A is not equal, then check the G bar, and A is less than B is like this combination of the whole complicated logic, and A is greater than B, then N exclusive or V, and A less than equal to B, then N exclusive or V, and H inversion. So all these kind of cases summarized in this table. As you can see, a little complicated for signed digit comparison. So signed mean and the input A and B is represented in two's complement, right? One number system. So MSB represents sign, right? In that case, we have to double check all these cases. I'm not gonna go over in detail about this, so you will just see how those works. The shifters is a very widely used building block for logic operation. So we have a logic 3 different example of the shifter logic. One is logical shift, and the other one arithmetic shift and rotate. The logical shift is a shift number to the left with filling in with the 0. For example, so left shift the logical shift right, then the shift to the right 1 0 1 0 1, right? So this one to the right, so empty one becomes filled in with 0. Logical shift to the left is 0 1 1 and 0, filling with the 0. For the arithmetic shift, we shift the number of shift to left or right, assuming this is a two's complement number. So to the shift left, shift right, we can have some value. So for example, so let's say shift right. For the case, this is a negative number, so we extend the sign. We assume that there is that 1 is extended value. So 1 1 0 1. This is shift right, arithmetic shift right. And for the arithmetic shift left, it's a little tricky here. This is a negative number. If you shift to left, then it becomes 0 1 1, right? So what we will add in this case, it should be 0 because nothing coming in. So the value becomes wrong value. But for the rotate, we are rotating bits to the left or right with the filling in with the lowest bit. For example, rotate to the right, so this one goes to here, and the lowest bit goes to the front, right? That one goes to the front. Rotate to the left as this one goes to the left, and then this lost bit will go to the LSB, so 0 1 1 1, right? The funnel shifter is the hardware structure that we can support all different kinds of shifts. So this is the basic things that we have a B field and M field for the input of the N bit. So 0 to N minus N is 1 is the N bit, right? So another N bit is allowed, is allocated. So total P plus, so total 2 N bits prepared, and by having different selection bit or shift bit, we select N bit out of this shift the input, this special 2 N bit arrangement. We can select a range of the sum of the portion and send it to the output. Then we can implement the all different kinds of the shift operation by adjusting the offset, right, from the left or from the right to the left. How much offset is there? So we give in the offset as an input, then we select the bits from the input B and C. We will see the example in the next slide. For example, if we start with to implement the logical right, we fill in B field with all 0 and C field for all input. Now, if we want to logical right by K, then we select the K from the offset. Let's say, for example, offset of 1, then we select A1 to 0, right? Here 0, AN minus 1, and A1 up to A1. Then we complete the logical right by 1, right? So we can have this kind of simple formation to implement the logical right by K. For the logical left, we fill in B field with the AN minus 1 to 0, this is input, and C field is all filled in to 0. What if we want to have a logical left by, let's say, 1, logical left by 1, then K become what? K becomes N minus 1, right? So we select the offset becomes N minus 1, so we are selecting from the MSB of the C to what? AN minus 2, right? Then logical left by 1 is then, right? You select that, right? So this is kind of a handy way to implement all these, like how many 1 2 3 4 5 6 cases we can fill in how we fill in the B and C and offset for different shift operation. So here, arithmetic right or shift, we put in the input on the C, and on the B field we extend this MSB to the B. This is sign extension, so we can select the offset K, so we can implement the arithmetic right by K, right? If the K is equal to 1, we select this A N minus 1, A minus 1 to the A1, right? For arithmetic left, B is filled in with the B input, and C filled in with the 0, and offset calculated by M minus K. The right operation, rotation is filled in B and C, both input, right? To the left, we filled in the same thing, and n minus k is the offset, right? So this kind of structure require n minus k, meaning additional adder or subtractor should be there to properly calculate this, perform the shift operation. We can further simplify the funnel shifter by having two n minus 1 input bit arrangement instead of 2n bit. In this case, the offset calculation is easier. Previously, we needed adder to calculate the n minus k, but if we reduce the bits, then we can just simply calculate by just inversion of the k. For example, logical left case, we have a input n bit and all 0 filled with the n minus 1 bit. In this case, by offset, we can select the input bit, right? 0, k equals 0, we select this, and k equals 1, we select the other one like this, 1 bit left, right? For the logical left, we've place the n bit to the left, and another O0 becomes n minus 1. In this case, k bar is there. If, for example, if we have logical left by maximum, for example, smallest one, let's say 1. If the logical left by 1, then offset becomes what? If the k equal 1, then the k bar become 1 1 1 1 1 and 0. So this is the maximum shift minus 1. So we select the n minus 1 to the first MSB 0, right? This is just a handy way to to calculate the offset. For the other all arithmetic right, we extend the bit by n minus 1 bit. This is n bit, right? The offset is input. The other case, offset is just inversion of the input, right? Optimize. So we can optimize this operation. Here, k inversion, and fill in with the, this is the n minus 1 bit, this is n bit, right? This is m is for the rotate right, we have n bit on the right, and left n minus 1 bit, right? This is an example of the funnel shifted actual implementation. We can use the you can make the make this using n bit n input multiplexer, n times n input multiplexer. For example, we have a y0 that is selected out of how many? 1 2 3 4 4 to 1 mux there. The input is 0 to G3, right? For y1, input is 0 1 G1 to G4, and etc., right? So for the control offset bit, this determine the amount of shift operation. We need to have capability of the inversion, right? For if that is inversion, so if the left shift left is selected, then we have to invert the k, right? Otherwise we just pass k. and then select decode select only one of, we have a selection signal here, we select only one of those selection signal, that gives us the shift operation. On the G field we have in this case 1 2 3 4 4-bit input, so we add additional 3-bit on the left to complete the funnel shifter structure. This path transistor with a single MOS will have a VTH drop problem, so we need a low VT device or some amplifier on the output to recover the logic level to VDD. This is a simple structure of the layout. This we have a MOSFET here and gate here, the selection signal here, right? Z signal like this and like that. If we place this unit cell by array, then we complete this kind of a left structure. Another way to implement the funnel shifter structure is just using 2-to-1 multiplexer. So like this, we have an input 7-bit, so actual input is 4-bit, but we have additional 3-bit to constitute the funnel shifter structure. And here decoder is in here. If the left operation is asserted, then this exclusive OR behaves like the inverter. So if the left is 1, then the K1 and then K0s are inverted. If the left is 0, then we pass K1 and K0 as it is, right? This is the property of exclusive OR is quite interesting, right? And if this is 1 and Y, then it is the same as inversion. If this is 1, control bit is 1 bit is 0, then this is equivalent to just buffer, just passing A to I. So we use this property to decode, to make the decoder signal. This is a binary shifter operation, so you can constitute a 2-to-1 multiplexer here, right? In this case, there's no select decoding needed, we just pass through the K value to the left, to the selection signal. But in the previous case, we had to convert the 2-bit. We got the 2-bit and we had to decode that S0, S1, and S2 and S3. We had to have such a decoder in the previous example, but in this case we don't need that.